Καλώς ήρθατε όλοι στο σημερινό σεμινάριο. Θα προλογίσουμε λίγο την ομιλητή στα αγγλικά, σε περίπτωση που υπάρχουν και αγγλόφωνοι που θα δουν την ομιλία αργότερα. Οπότε, we are very happy to have Dr. Georgakakis today with us. And a few words about Antonis. He received his PhD from the Imperial College of London in 1998. And since then, he has worked as a research associate, both in the University of Birmingham first, and then at the National Observatory of Athens. In 2008, he moved back to the UK, after having received a prestigious fellowship, which is the Marie Curie Fellowship. And after that, he joined the high energy group of the Max Planck Extraterrestrial Physics Institute in Munich, in Germany, where he worked. He joined the group in 2011, and you stayed there, Antonis, for several years, like 7, I believe. And after his stay in Max Planck Institute in Germany, he decided to come back in Athens, where he became a permanent senior researcher at the National Observatory of Athens. So Antonis is an expert in X-ray astronomy. He is mostly interested in the observational study of active galactic nuclei using X-rays. And today he has worked a lot on the study of AGN in high redshifts. And also he has worked in the modeling of the spectral energy distributions from AGN using different statistical tools. So today he will be talking about forward modeling the energetic universe. And we are very happy to listen to what you're going to say.
Thanks a lot for the introduction, and it's a pleasure to be here. After a few years, it's good to come back. I graduated from this university and actually this building probably maybe 30 years ago, but it's great to be back. And so today I will be talking about modeling, but as Maria said, I'm more from the observational astronomy, and therefore I will approach the modeling from the observational side, and I will be talking about empirical models of AGN. So the presentation is about supermassive black holes at the centers of galaxies, and the questions that I will discuss in the next 45 minutes or so have to do with the physical processes that activate those supermassive black holes that we know exist at the centers of galaxies. So a few words about motivation. We know that in the universe that most of the galaxies, at least the massive ones, they have the nuclear region supermassive black holes. And we know that those supermassive black holes accrete their mass or grow their mass by accretion predominantly. And therefore the question is, what is triggering those accretion events onto supermassive black holes? And this question is important because if you take a snapshot of the universe at almost any redshift, and you count the number of galaxies that have an active supermassive black hole at their nuclear regions, those are the active galactic nuclei, by the way, the AGN. So if you count the AGN in your volume, they are really a minority, right? Most of the galaxies, although we know that they have a supermassive black holes at their nuclear regions, those black holes are biased. So we need to understand this duty cycle, why some have and some don't. And what I will argue in this presentation is that one approach for addressing this question, this theme, is to link AGN with galaxies, link active supermassive black holes with the properties of their host galaxies. And in this approach, one can look at the parameter space of galaxy properties. Some of them are shown there: star formation rate, stellar mass, environment, morphology, and look where in this multidimensional parameter space the incidence of AGN is the highest or the lowest, right? And therefore, I identify extremities in the parameter space which would indicate a preference, an environment, or a region of the parameter space where supermassive black hole accretion events proceed more efficiently and can be interpreted in terms of physical processes. And I will kind of demonstrate this in the next few slides. This kind of approach, by the way, requires population studies. It requires large samples of AGN and galaxies. I will discuss a little bit of that as well later. In addition to those observations, one needs models to interpret the results. And there are many models out there in the market, semi-analytic models or hydrodynamical simulations, all sorts. But in this presentation, I will be talking about a particular class of models which fall under the umbrella of semi-empirical models. And the comparison of those simulations with the observational data in the presentation will be done in a forward modeling way. I will explain what that is later on. And the argument I will make is that this semi-empirical forward modeling approach provides very good handle on systematics and observational selection effects, which are massive in this particular research. Right, and I will demonstrate all those points with a particular science application, which has to do with the environment of AGN. The question I will be asking is, does the environment play a role in modulating accretion events onto the supermassive black holes of galaxies? So I will start with this plot, which shows observationally the evolution of the AGN population as we understand it today. What you see in this diagram is black hole growth rate density. It's a measure. It's a measure of the average black hole accretion rate, average over cosmological volumes at different redshifts or cosmic times. So this quantity there is plotted as a function of age of the universe or redshift at the top. And what you see essentially is that there is a very strong evolution of the AGN population. If you start from redshift 0, which is low, this particular quantity, this particular statistic, increases rapidly up to redshift of about 1.2. Then there is a broad plateau up to redshift of about 3. And then we don't know exactly what is happening, right? I mean, there are suggestions that, above redshift 3, the incidence, the space density of AGN decreases, and we are witnessing the formation of the first black holes. But this is really, redshift above 3 is really the area of JWST. And already JWST is probably providing data that will change maybe the picture that we have above at very high range. The main point is that we have been studying the evolution of AGN for very many years, right? In the last 20 or 30 years, there are numerous studies that have been trying to put data points in this diagram. And therefore, we understand this evolution, at least up to redshift of about 3. We understand this evolution very well. We know what the AGN population does in terms of population, in terms of numbers, right? What we don't understand very well is what is driving this evolution. Why do we see this rapid increase up to high redshift? And this is what this presentation is all about. And I would argue that in order to understand that, in order to understand what is causing the evolution of black hole accretion rate density, we need to study AGN in the context of galaxies, right? So we cannot consider supermassive black holes as independent of the galaxy in which they belong. And this is because, of baryonic physics, really, and how galaxies form. So we know that the main sites of galaxy formation are dark matter halos. And those dark matter halos, what they provide is essentially a gravitational pull, the gravitational potential well within which baryonic matter can condensate, can fall into the potential well and form luminous structures like galaxies, for example. And the physical processes that are relevant in this galaxy formation scenario are very many and very complex. Right? You have gas cooling or heating, you have flows of gas from large scales to the center of the of the dark matter halo. There is the formation of new stars, feedback processes, various feedback processes. And one of those baryonic physics processes is the formation of supermassive black holes at the center of the galaxy. And we know that when those black holes are active and they accrete material from their surroundings, they produce large amounts of radiation. This radiation can affect the interstellar medium of the galaxy that it belongs to, and therefore affect its evolution. So the formation of galaxies and the growth of supermassive black hole is not really independent. They are two processes that need to be studied in conjunction, and therefore it is important to study the host galaxy properties of AGN. Now, there is merit in choosing individual AGN and studying them to death. There is definitely things that can be learned from this approach. However, intrinsically, the accretion process into a compact object is a stochastic process, and therefore population studies are essential to average out and oddities and come out with average trends. So it is important not only to study galaxies and their host galaxies, it is also important to do population studies. And this is the case where you have large cosmological volumes. You select galaxies in those cosmological volumes, you select AGN, and try to understand, what is if there are systematic differences of the AGN population relative to galaxies. And I will demonstrate this point with this cartoon here model. So this is a cartoon model that states that AGN are triggered during major merger events, right? So the cartoon says that you have like two galaxies that start interacting, then they eventually merge. And during that process, the supermassive black hole at the center of the system is igniting, switching on. And therefore, you have like a luminous AGN and QSO shining at the middle, at the nuclear region of this system. And the energy produced by this event, this accretion event, can generate outflows, AGN winds. Those winds can regulate the formation of, the flow of gas to the nuclear regions, and therefore eventually stop this process. And you end up with a merger remnant with a quiescent. So this is a possible scenario for the formation of supermassive, for the triggering of AGN. Now, how can we test that? Well, there's a clear prediction. And that scenario clearly predicts that if that's the dominant mode of black hole formation in the universe, then one should expect a correlation between morphological properties of galaxies and the incidence of AGN, right? In particular, you may expect to find AGN, as I said, in galaxy pairs or in galaxies that show morphological disturbances suggestive of merger ongoing interaction. And this prediction can clearly be tested with observations. If you go over there out in the sky, select a sample of AGN, and such a sample is shown here on the right. This is selected at hard X-rays in the local universe. And then you simply study the morphology of those AGN. And what you see in these pictures is that many of them are actually associated with ongoing mergers, right? You see morphological disturbances, galaxy pairs, the full Monty, right? So this is an observation which supports this scenario. Now, I'm not going to go into the discussion or debate on whether mergers are relevant for black hole growth or not. But what the point here is that if you have a model that makes clear predictions, you can have you can go to populations of AGN and test those predictions, and that's what they will be doing in the next slides. However, there is a big caveat with this type of studies, and the caveat is that first of all, the parameters that we think are important or are relevant to black hole growth are highly correlated. So properties of of host galaxies that may be relevant to provide information about the conditions in the galaxy and the growth of black holes have the star formation rate, stellar mass, the environment, the morphology that I just showed you. All of those parameters are correlated, right? We know observationally that there are intrinsic correlation, or there are correlation between all those parameters. And therefore, it is difficult when you do such an observational study of population. Sometimes it's hard to disentangle, underlying correlations from true signal, right? And the situation is made even worse when you have selection effects, observational selection effects to go on top of that. For example, observations typically are flux levels, there are uncertainties, and so on and so forth. And combined with covariances, it makes the interpretation challenging, right? And there are two approaches, or many approaches really, that one can follow to address this caveat. One of them is to define control samples of non-AGN that follow similar selection criteria as your AGN sample. So they have similar observational selection effects, but they are not AGN, and therefore, when compared with the AGN sample, any systematic differences can be interpreted, right, in terms of physics. But what I will propose here is this forward modeling approach, and I will argue that is, a competitive way of actually moving forward, addressing this caveat, and moving forward with understanding triggering mechanisms in AGN. What is forward modeling? Well, this is the approach where you have if you can build a model of your AGN and galaxies in the universe, right? Under certain assumptions, then you can take this model and generate observables, generate observations. And those observations or observables can have any selection effects, but also affect real data, real observations. And then you have your mock observation, you have your real one, you can compare the two. And if there are differences or agreement, you essentially test your assumptions that go into the construction of the forward model to start with. So this is the forward. So take your model and bring it to degrade it to bring it to the level of your observations, and then do the comparison between model observation, model predictions and observation there. And the reason that this is quite interesting is that because you put the selection effects by hand, right? You have a very good control on those. So it allows you to do hypothesis testing with a very good control on observational selection effects, which are massive, right? Okay, well, that's all great, but then the question is, how on earth do you build a model of AGN and galaxies in the universe, right? Which is a major challenge. It's not easy. Of course, there are many models, like semi-analytic models, hydrodynamical models that try to do that, try to reproduce the evolution of AGN galaxies in the universe. The problem with those models is that they have so many parameters to control, right? And sometimes, if you have so many parameters, you can do anything you want. I will argue that an alternative approach is empirical method. You rely on observational correlations, and you build a model based on that. Right, and because there is this connection with the observation, the number of parameters that need to be tuned or fit is not that many. And why can we build a model of AGN in cosmological volumes? Well, essentially, this is because, first of all, nowadays we have a huge number of extragalactic surveys, multi-wavelength extragalactic surveys. And this is great because the surveys, like those ones listed here, they provide information about galaxies, AGN, as well as the host galaxies of the AGN. And this is because they cover because of the multi-wavelength nature of those observations. And the key parameter, I will argue, that is is important here is this specific accretion rate, which is defined here there at the top. It's just lambda is the ratio between the AGN luminosity divided by the stellar mass of the host galaxy. And if you like, this parameter provides a measure of how many AGN photons are emitted per unit stellar mass of the galaxy. And under certain assumptions, this parameter can be interpreted as Eddington ratio. It can be interpreted as Eddington ratio because there is a known correlation between stellar mass of galaxies and the black hole at their center. And therefore, this kind of provides a proxy of how fast a black hole accretes relative to the maximum, which is the Eddington ratio, right? So this is the key parameter that can nowadays be estimated from observations for large samples of AGN. What is also important about this parameter is that it includes this stellar mass. That means that you can place AGN within the galaxy population as follows. If you go to a particular stellar mass interval and count how many galaxies you have, and then in the observations, and then simply count how many of those galaxies are AGN, suddenly you have an incidence, right? You have like the probability of the galaxy in that particular stellar mass being active, right? And therefore, you can build what is called the specific accretion rate distribution. That is shown on the plot there. I will explain what it is. And those distributions are purely observationally derived, right? So they are empirical probability distribution functions. So what it is, on the vertical, well, you see the 4 panels. Each of those panels correspond to different redshifts. The vertical axis is the probability, right? Is the probability of a galaxy hosting an accretion event of a particular amplitude, if you like, of a particular specific accretion rate, right? And this is plotted as a function of the specific. And if you look a little bit at the shape of those curves, so there are many observational results from the literature. I think the golden or green or yellow curves correspond to the state of the art. This is work by Brivael Lalou, who is a PhD student at Observatory. If you look at the shape of those curves, it's kind of expected, right? So the probability of very high specific accretion rate events, right? High Eddington ratios is very low. You have very low probability of a black hole accreting very fast. But if you go to lower specific accretion rates, or lower Eddington ratios, then the probability increases. So it's more probable for such events to happen in black holes. And curves like this, like those, have been studied a lot in the last 10, 15 years in the context of AGN triggering mechanisms. What can we learn about the triggering mechanisms by just simply looking at the incidence of AGN in different galaxy groups? But what is relevant for this presentation is the fact that those curves are probability distribution functions, right? What that means is that if you have a group of galaxies, like the blue dots that are shown there at the bottom, and you can use those curves to assign AGN in those galaxies in a probabilistic way, because they're probability distribution functions, right? And therefore, suddenly, if you have a sample of galaxies, you can end up with, you can paint AGN on them, right? And this painting business mathematically can be expressed as the convolution of the stellar mass function of galaxies with a specific accretion rate distribution to produce the AGN luminosity function as output. So this is those three squares at the bottom. This is what they show essentially, and therefore your mock AGN sample can be produced. And the fantastic thing is that certain properties of the AGN population, statistical properties of the AGN population, are reproduced by this process by construction. And one of the key properties that is reproduced by construction is the space density of AGN at different redshifts. In other words, that's the luminosity function of AGN. Okay, so So these three squares there is the core of what I will be discussing later on, is the core of the semi-empirical model that I will be building. And I should also say that this is, the semi-empirical modeling is very modular thing. Once you have your core of the empirical model, then you can add different modules on top of that and make different predictions. So it's possible to make an SD module, add it to the AGN generation module, if you like, and then suddenly you have multi-wavelength properties of AGN and galaxies. And this is kind of shown there. What you see at the top is the mid-infrared color magnitude diagram. The details don't matter really. The blue points is the mid-infrared population. The red dots are AGN selected by some criterion that is observational and derived criterion that is widely used in the literature for finding AGN in the mid-infrared. On the left, you see the real observations. On the right, you see the mock, what is generated by the semi-empirical model, the empirical modeling. And you can appreciate differences and similarities, right? What can be done. But I'm not going to talk about that today at all. This is just a demonstration of the modularity of the empirical modeling. You can also do other things. You can link the core of the empirical modeling with a variability module, and then you can predict the flux variability of AGN. So flux variability is a fundamental property of any accretion process. And this is demonstrated on this figure image there on the right. This is a sequence, a time sequence of observations at X-rays at a particular part of the sky, the chunk that fills out. And if you look hard and long enough, you can see AGN flickering, right? All the point sources, all the bright sources that you see there are AGN, and you can see them flickering. This is the variability, provides a lot of information about the central engine. And it is possible to quantify statistically and also interpret in the context of this semi-empirical model. And the bonus is that turns out that if you model the variability of AGN, you can learn about fundamental correlations, such as the stellar mass, black hole mass relation. But I'm not going to talk at all about that. What I'm going to talk is this. How can we take this empirical model, add a cosmic web module to it to predict the distribution of AGN on the cosmic web, right? So you see the cosmic web there on the right as traced by galaxies. This is coming from a simulation. You can see cyan dots on that. Those are AGN, mock AGN generated by the empirical modeling I am talking about. And they are not just randomly placed there, right? As I will show you in a bit, there is a process by which you assign AGN to galaxies, as I will show in a realistic way, right? And the question that can be answered with such modeling is, does the position of the cosmic web affect the activity of galaxies at the nuclear regions, right? So do we see evidence for environmental effects in triggering accretion events onto supermassive black holes? Before I go into details, a few definitions. First of all, what does environment mean, right? So environment can mean many things. In this particular presentation, environment means mass of dark matter helium. And we have phenomenological measurements observationally. We have phenomenological estimates of the density of the environment that the galaxy is located at. We have clusters, we have groups, we have voids, filaments, all of it, right? And there's a clear correlation between dark matter helium mass and those phenomenological measures of environment. I will be using in the rest of the presentation helium mass, okay? And there are a couple of scales that are probably worth mentioning. So when we say groups of galaxies, when we identify groups of galaxies, we typically talk about dark matter halos of 10 to the 13 solar. When we talk about massive clusters of galaxies, we talk about halos with mass about 10 to the 14 solar, right? So those scales will come into the presentation later on. Is there evidence that the environment play a role in the activation of the supermassive black holes at the centers of galaxies? Yes, there is. And that's why it's worth studying and modeling the large-scale environment of AGN. People have been studying the typical environment, and I underline here typical. It will become important later. So the typical environment of AGN using what is called clustering, right? So the details are not important. But what is important is that it is possible through observations to estimate the mean dark matter halo mass of AGN. And this is plotted here. This is the mean halo mass of AGN as a function of AGN luminosity. The data points are different measurements from the literature. So groups have selected different AGN samples, and with various, they have been able to measure from those samples the mean halo mass of the population. And what was interesting was that many of those data points are above this 10 to the 13 scale that defines the group environment. And that was kind of a surprise, 10 or 15 years ago, because people thought that if AGN, if the mean halo of AGN is 10 to the 13 solar, then that means that the typical environment of AGN is the group scale environment, and therefore processes like interactions or mergers may be important for triggering AGN activity, right? But what I will do in the next slide or two is question these results, right? To what extent do we really, do those data points provide evidence for that? But indeed, the typical environment of AGN is 10 to the 13 solar. And in order to question these results, I will use the forward modeling approach and the semi-empirical approach. I will construct an AGN mock catalog in the universe under the very simple assumption that the activation of supermassive black hole is simply a stochastic event, right? And that means it is agnostic on the halo mass of in which the galaxy belongs. So it's independent of the halo mass. And under this simple assumption, I will then generate mock observations. From those mock observations, I will use exactly the same methods used by astronomers, observational astronomers, to measure the mean dark matter halo of the AGN population, and then compare results, right? And by comparing, essentially you test the assumption AGN are a stochastic process that doesn't know anything about environment. Now, how can you build essentially this cosmic web module, right? So you can put AGN in the cosmic web. Well, this is based on cosmological and body simulations. Those simulations describe essentially the evolution of dark matter in the universe. So because this is only gravity, we understand it pretty well. We can accurately enough describe how dark matter condensates, forms structures as a function of time, starting from some initial conditions. Now, that's not enough. We need to place galaxies and AGN in those dark matter halos. And the way that galaxies are associated with dark matter halos in this particular work is via what is called abundance matching. Now, abundance matching can mean many things, but the simplest scenario is that the most massive galaxies are associated with the most massive dark matter halos. A very simple assumption, but it turns out that it works exceptionally well in reproducing the observable properties of galaxies. So this is what will be used in this presentation to go from n-body simulations to galaxies and stellar masses, right? And then once you have, well, this is the same shown graphically. You have your dark matter halo box and body simulation. Abundance matching takes you to stellar masses in galaxies, shown in the middle. And then if you use your specific accretion rate distributions, you can paint AGN on those galaxies under the assumption that, like they don't know anything. The probability of a galaxy hosting an AGN is independent of environment, is independent of hellos. So you can do this. And then once you have this mock AGN universe, you can build mock observations. Those mock observations sometimes are called light cones. You can generate light cones of simulated galaxies and simulated AGN. Those mock observations, those light cones, contain selection effects that are identical to those of observations, right? And therefore, you can use those mock observations to measure the clustering of AGN the same way we do with real ones. And this is essentially shown here. The statistic to measure the clustering of AGN is called the correlation function, the projected correlation function. It doesn't matter really what it means. The important thing is that the more positive it is, the more clustered the matter is, or in other words, the distribution of matter in the universe, in this case AGN, deviates significantly from the random distribution, right? So the correlation function measures deviation from randomness or clustering of matter. And the correlation function is plotted as a function of scale in this particular plot, and the black data points are the observations. So observers have identified the sample of AGN, and they have a recipe for estimating this correlation function, and they get the black points. From those black points, you can estimate also with appropriate modeling, you can also estimate the mean hello mass of the population, of the AGN population. And it's points like those ones, like those black points, that lead to the determination of average dark matter hello masses for different AGN samples. And what is shown with the red shaded curve in this diagram is the prediction of the semi-empirical model that I have been describing in the previous slides. And you can see that the very simplistic assumption of stochasticity, the fact that AGN do not know anything about the environment of the dark matter halo in which they are embedded, does a pretty good job in reproducing the observations, right? And therefore, well, there's a depressing result coming out of that, and there is an interesting result. The depressing result is that by studying, with this type of observations, we cannot learn anything about the activation of supermassive black holes. Because the model that assumes no physical connection between environment and the activation of supermassive black holes already does a pretty good job, right? That's the depressing result. The interesting result is that if the model is doing so well, we can learn, we can ask the model, what is the typical dark matter halo mass of the population, and whether it is the group scale or not, right? It turns out it's not, right? So here on the right, you can see the halo mass distribution of the mock AGN that reproduce this particular observation, right? Observational result. You can see like kind of Gaussians with a very long, a very pronounced tail towards very high halo masses. But the important is that the mode of the population where most AGN are is at about 10 to the 12 solar. It's not 10 to the 13. But the mode and the mean of this distribution are obviously very different because of the skewness. And this is why observational studies that have been trying to measure the average of this distribution have been finding results that are skewed high compared to the mode. Right, so yeah, that's what the model predicts anyway, that the typical environment of AGN is not 10 to the 13, but it's really 10 to the 12. An interesting fact about 10 to the 12, I don't think it's very relevant to this presentation, but it's interesting, I find it interesting anyway. 10 to the 12 is the mass of the halo of our own local galaxy group, right? So Milky Way and the Andromeda, they form this group, as we call it, and the total mass of the system is about 10 to 12. So our solar system, our neighborhood, is the typical environment where AGN actually happens, right? And you can think of connections between that and the Fermi bubbles, for example, that come from that we have observed in the Milky Way, and probably they tell us about past accretion events onto the supermassive black hole of our own Milky Way. Okay, so right, what I have said up to now is I have left the impression, I think, that the environment may not be important for the activation of supermassive black holes, right? The position of AGN on the cosmic web is irrelevant to whether a galaxy, the black hole of a galaxy, is active or not. However, we do know that if you look at the densest structures in the universe, and those are galaxy clusters, right? The evolution of galaxies in those environments, not the AGN, the galaxies in those environments are drastically different from the evolution of similar galaxies in less dense. We know that. And therefore, it's natural to ask, right, I mean, okay, so maybe the large-scale distribution of AGN does not tell us much about the activation. But how about if we go to the densest structures in the universe, to clusters? Do we see evidence there for physical processes that modulate the accretion onto the supermassive black holes of the galaxies in such environments? And physical processes that may be relevant here are some are listed there: ram pressure, strangulation, harassment, all those different jargon. Right, and yeah, so the way I will approach this problem, right, is very simple. I will just observationally, I will just simply take clusters, identify AGN that belong to those clusters, and simply take the ratio between number of AGN and number of galaxies. And as I will show you, this very simple statistic is quite powerful in telling us about the activation process or the modulation of black hole accretion events in clusters of galaxies. So this is shown here. In this plot, the vertical axis is the fraction of AGN in clusters. Number of AGN divided by number of galaxies. The horizontal axis is redshift. So you see three sets of points there: low redshift, intermediate, and high, where high here means redshift of about 1. The relevant look back times or age of the universe really are also shown. And you can see two sets of the data points, by the way. The stars are observational measurements. So people have been doing that, isolating clusters of galaxies, measuring how many galaxies there are there, measuring how many AGN, and taking the ratio. And you can see two sets of points. The blue is for very luminous AGN. The red is for moderate luminosity AGN. And of course, modeling comes into play as well. The semi-empirical modeling that I have been describing previously is used to interpret those observations, right? And you see two curves, the blue and the red. The blue curve should be compared with the blue data points. The red curve should be compared with the red data points. And the assumption of those curves, again, is that the incidence of AGN in clusters of galaxies is independent of the halo mass, right? So whether a galaxy has an AGN in those dense environments or not knows nothing about the fact that it's such a dense region of the universe. And maybe I will draw your attention, first of all, to the red curve and the red data point at very low redshift, right? Redshift of about 0.2. And you can see that the model, the red curve, overpredicts the observed fraction of AGN in clusters of galaxies. And that means that there are more AGN in the model than in the real observations, which means, again, that there is suppression of AGN activity in clusters compared to what the model predicts. In this particular case, at low redshift, the zero assumption of the model that the incidence of AGN in clusters is independent of environment can be rejected, right? At these environments, at low redshift, AGN activity should be suppressed in dense environments. And then I'm going to draw your attention to the blue curve and the blue data point at very high redshifts. You can see in this case that the model significantly underpredicts the number of AGN in massive clusters of galaxies at high redshift. And this is surprising. It means that in these environments, there are more AGN than the model under the simple assumption can produce, right? So this indicates that clusters of galaxies at higher redshift are very active environments in terms of nuclear activity, black hole growth, right? And then it is interesting to speculate or discuss what kind of physical processes may be responsible for this particular excess, right? So what is causing this excess of AGN at high redshift galaxies? I will talk about, well, Ram pressure and interactions of the two processes, possible processes that may be relevant there. Now, Ram pressure sometimes is associated with the suppression of AGN activity or the star formation activity in galaxies. This is because Ram pressure is essentially pushing away the gas of galaxies as they fall into a cluster. Nevertheless, there are observations and simulations which suggest that under certain conditions, right, Ram pressure can initially suppress the gas of the nuclear regions of galaxies and therefore promote AGN activity. So under certain conditions, this may be responsible for the excess for the high rate of AGN activity that we see in high redshift clusters. However, those two processes, if they are in operation, then they may be more efficient as galaxies fall into the cluster, right? So the galaxies continuously join the cluster through the cosmic web, and those processes may be more efficient in igniting AGN in those galaxies during the first fall, before they merge with the cluster. And there is indication that this is indeed happening, observationally at least, and this is shown here. So this is observational evidence for the activation of supermassive black holes as they fall onto a cluster. So what you see there on the right is a cluster of galaxies, X-rays. The dark pink in the middle is the extended gas emission, high temperature gas that is emitting at X-rays off the cluster, and that's how we know that there's a cluster there. You can see very many small point sources in this image. All of them are AGN, or most of them are AGN. And what has been highlighted is this ring around the cluster. This is approximately the virial radius. A little bit. This is this ring around the cluster is close to the outskirts of the cluster, right? It's info region, if you like, of the cluster. And with small circles, a number of point sources, most of them AGN, have been highlighted. And the reason that they have been highlighted is that if you take the radial distribution of AGN in this particular cluster, so if you take rings and you count the AGN in those rings or the X-ray sources in those rings, you can build this distribution here. This is the radial distribution. So which shows how many AGN do you detect at different rings around the cluster. And you can see this clear excess here of projected excess of X-ray sources. This radius where this happens is this one, the red data points corresponds to this ring. And this result has been interpreted as direct evidence for activation of the supermassive black holes of galaxies in the info region of clusters. However, there is a big, right? And the big caveat are projection effects. This is a projected radial distribution. We know nothing about the distances of those galaxies, of those X-ray sources, relative to the distance of the cluster. We don't know if they are member clusters. And it can be that projection effects, so structures behind or in front of the cluster, the cosmic web essentially, may be able to produce such an excess. And this is exactly what we set out to test with the forward modeling that I described. And the test is shown here. So again, you can set up your model under the assumption that there is no relation between activation of supermassive black hole and environment, and you can make predictions. You can take this model and make predictions that take into account all the selection effects that go into these observational results. The depth of the X-ray observations, the mass of this particular cluster, all of them can be incorporated into the modeling. And when you do that, the colored curves here, the colored lines here, is the prediction of the model, right? And this is the mean prediction of the model. When you have such a model, you can build many realizations of that cluster. And therefore estimate an average. And you see that the lines, the colored lines, are flat. They cannot actually reproduce this excess of projected counts, right? The observations here again are the black points. It's the same black points as shown. All right, so at first sight, the model fails. However, what you also notice from this plot is the shaded regions. And the shaded regions around the mean is the sigma, the standard deviation, is the scatter. And the scatter, in this case, is dominated by cosmic variance, by sample variance. The fact that when you have light cones that point to a cluster, you also sample the cosmic web in the foreground and the background of the cluster. And it can happen that in those sight lines, very, very dense regions are included. And this scatter here is exactly that, this sample variance. And it turns out that if you take the scatter into account, you can produce realizations that look exactly like the observations. And this is shown here at the bottom, right? So the black data points is, again, the observations. The red line is a particular realization of the model, not the average, but a particular realization. You can see how well it reproduces the observations. And the thing is that for this particular realization, because it's a model, we can ask the question, AGN in this peak, in the projected radial distribution, where do they lie in redshift space relative to the redshift of the cluster? And this is essentially shown here. This is the redshift distribution of all AGN in this particular ring, radial ring. The redshift of the cluster is shown here with a vertical line, and the red line is the model redshift distribution. And you can see all the AGN in this case are a background structure, a structure at a very much higher redshift. And this kind of setup, this kind of realization is not happening very rarely. 20% of the realizations that can be done with this forward modeling have like this type of structure, right? Background and foreground structure just falling within the field of view. I'm going to stop here. I hope I have convinced you that forward modeling provides an interesting way of studying the population properties of AGN and help us learn about triggering mechanisms of black hole accretion events. There are a number of things that we learned on the environment of AGN. First of all, that the typical environment of AGN in the universe are similar to our local group. Massive clusters of galaxies appear to promote AGN activity at high redshifts, and based on the results that are on the discussion I just did within the previous slides, evidence for activation of black holes during the infernal clusters is controversial. And I'll stop here.
it's time for questions now. Thank you very much for that. Very interesting talk. Yes. And I thought about it, thank you very much, very exciting. I wanted to ask you, if we go back to the example with the excess appropriations, which is about the bigger range, we said, okay. I think even looking at the top diagram, the difference is just 1.5 sigma.
Right, yeah.
Yeah.
Right.
Yeah. So even looking at that, it's just one object. You don't expect that to be estimate. So the way to go about it, okay, you showed it also in the way with the forward modeling you did. Yeah. But if there was any way of getting redshifts of these things, then you can solve this.
Yeah.
For good. And second, if you have more objects, this is just one observation, one cluster, right? Then you have observations, probably you have observations for more than one cluster.
Yeah.
More than one? How many?
So the original paper that proposed this thing, they have a total of 5 clusters.
Okay.
Now, and they see this type of excess in the claim was 3 out of 5.
The other part, were they always the data rate?
Yes, that was the like
Because
the
I
unexpected
expect it to be just from, just from projection effects.
if it is systematically
Yeah.
associated with
Yeah.
absolutely.
So
Yeah,
if it's not cases like the bigger, okay, it is a small number, but
exactly.
for a bigger sample, you find always at the bigger ranges you have this. Then it cannot be a.
So there are 2 ways to approach this problem, right? I mean, the one spectroscopy is the obvious one, and this yeah. So we are pursuing that. The other is say, all right, so the simulation predicts 20%. So if I take a large enough sample and the fraction of age of clusters that show this type of behavior is statistically significant for this 20%, then maybe it's physical. And now the argument made by the authors of that work is that what is important for doing that is to have a very good knowledge of the hello mass and what is called their R500 virial radius, different measure of the radius of the cluster. And this is not easy. It needs very careful modeling and good signal to noise, lots of data and all that. So they only had, at the time, they also had this quality of data for only 5 clusters. But since then, we have been looking into significantly larger number of the order of 60. Now, not all of them at high redshift, they are spread over different redshifts, but yeah, I mean, if you systematically see the same effect in those clusters, then the fraction that show this excess significantly larger than we are significantly different from 10%. Then maybe there's a case for it.
What will you make your mock? One more question. When you make your mock clusters, let's say, you can you know where the video is. So you have a label for each of these realizations. You know if the peak, if there is a peak, if it exists on the video range. They have to account in the bias. Oh, this is 20% of what you say. I mean,
yeah, exactly. So this is the top is the average.
Yeah.
And the scatter from realization to realization.
It's for that particular range.
It's that, well, the black points are the observations.
Yeah.
The scatter is just a shaded region.
Yeah.
So what that scatter tells you is that if you have 100 realizations, 68% of them will be within that region. Or 68 of them will be within that region. But then you can go to individual realizations, right? So this is the average, and then you can look at individual realizations and also have quantitative criteria of defining whether a simulated distribution matches or not the data. And then in 20% of the cases, you get that. You get something like that.
Can I ask something about that? Very relevant. For those realizations of the master data, have you also tested if all of them are like in a ring kind of structure, or they are clustering part of the ring? Because the actual observations show that like a very good symmetry that all the sources are spread equally around a certain ring. I guess that
If there is
maybe they are clustered in one part of the ring.
Yeah, no, I haven't looked at that. I mean, in that simulation, any excess is because of background galaxies. By construction, the model does not reproduce a peak at a particular edge. There's no physics there to reproduce such a peak. So because it's background or foreground, yeah, maybe you should expect some clustering within the ring, but we haven't tested. Yeah.
I was wondering, what is the radius of the cluster in this case? Like, we can see the redshift, but what is the radius of the cluster that we're talking about? So,
in physical units?
Yeah.
Yeah, I mean, we're talking about around 1 megaparsec. So this is close to the virial radius. So there are variations depending on clusters from cluster to cluster, concentrated they are, so on and so forth. But typically, you're talking about 1 megaparsec. That's the virial. That's not R500. R500 is a little smaller than that, maybe fraction of 1 megaparsec. But the virial radius of clusters of this mass is typically about 1 megaparsec.
And on this example, the redshift of the cluster is 1, right?
Yeah, exactly. So this is how the simulation is set up. The simulation is set up so the cluster is always at redshift 1. This is because the real cluster is also at redshift 1, at the same redshift. And we always, in the simulations, what is done is you view this cluster from different angles, if you like, from different observers. And that's what makes the different realizations. So different observer, you have your cluster, particular place, particular distance from your observer, you just rotate your observer around it. And by rotating the observer, you sample different parts of the cosmic web.
I'm not really sure that I can understand how the source, the redshift that we have the peak, is not the same as the cluster.
Well, you have to. So if you look at the cosmic web, right? I don't know. There's a good picture, right? Suppose I don't know that your cluster is this one over here, and your observer is back here somewhere. And therefore, as he observes the cluster, he picks up this massive structure at the back, which is at a different redshift, however, right? It's in the background. And therefore, within your line of sight, it's not only the massive cluster that you're observing, but also background structures of the cosmic web, right? So but your observer may also be located somewhere here, right? And then if it looks at the same cluster, it looks through voids. It doesn't look through dense structure of the universe, right? This is, I don't know, you can find sight lines that, contain only voids, or sight lines that contain rich structure. And, when you build your simulation, you have full control of that. You can place your observer anywhere you want, randomly, as is done.
So I have a question about the specific accretion rate distribution. I don't quite understand if this has been constructed, like the observational one, using galaxies and AGN that do not belong in cluster.
Oh, yeah.
It's like a field kind of.
It is, yeah, it is. Because, clusters, and to some extent groups as well, are very rare. right? So if you do, you have all those extragalactic surveys, some of which are designed to avoid trips areas of the universe, right? So the chance of having a cluster in one of them, a massive cluster, is very low. And even if you do, the majority of your AGN population is outside. So essentially, those specific accretion rate distributions, yes, they are observationally derived, but they kind of represent the field population. They are representative of average density environments where average, I don't know where it means. I think it means 10 to the 12 solar. Because that's, I don't know, I mean, yeah, it's a sweet spot, right? Because in that kind of halo, you have massive galaxies like our Milky Way. If you go to smaller halos, then you don't have massive galaxies anymore. You have a difficulty detecting them as AGN, so on. So this is kind of, and also in more massive, in less massive halos, baryonic physics become more important. The supernova explosion, stuff like that, become more important, and therefore, yeah. So 10 to the 12 is kind of a magic number. It is also where the star formation rate peaks, right? This is the environment where the star formation rate proceeds more efficiently as well. And I think it has to do with that, really, baryonic physics.
And one more, if I can. So,
No.
one more. So based on your probability modeling results, you showed that the environment does not play a role in activating the AGN, at least up to redshift of 1.
Yeah.
So, in your opinion, what is the main physical mechanism for triggering AGN?
Yeah.
Because mergers cannot make it, or basically they should not be as frequent in determining the activation of AGN. Finally, the dark matter halo density, or the density of the halos does not play a role. So what is it?
Yeah. So, I mean, I think one has to understand that AGN activity is stochastic. What that means is that you have a tendency for some galaxies to promote accretion events, but it's only on the average, right? So there's a probability distribution function of a particular class of galaxies to have the black hole active at any given time. I think, yeah. And then the question is, what should the conditions be for that to happen? What is this class of galaxies? What are the properties of this class of galaxies where, on average, they tend to be more active in terms of nuclear activity? And I think I don't think we have a clear answer to that, but I think it's clear, I think, that you need gas. You need some gas supply. If you don't have a gas supply, then, yeah, I mean, there's nothing to fill the black hole with, right? And therefore, one indication of gas availability is star formation. When a galaxy can form stars at a high enough rate, then there is some amount of gas. So gas availability as probed by star formation rate, I think, is a requirement. And we see that, like if you study the incidence of AGN in star-forming galaxies, it's higher compared to passive galaxies, for example. However, it's not zero in passive galaxies either. We do see AGN in quiescent galaxies, which is, like, it's hard to understand how, right? There are suggestions, but it's a little bit counterintuitive in the sense that, those passive galaxies hardly have any gas, right? But nevertheless, they can sustain black hole drift. But again, I mean, the probability of those galaxies hosting an AGN is lower than star-forming galaxies. And then in star-forming galaxies, where you have gas, mergers, interactions do play a role. I don't think that there's doubt about that, but it's not the dominant process. You have all sorts of, mechanisms that fall under the normal galaxy evolution umbrella, right? Like the formation of baps. It's a stochastic process as well. Some galaxies just form baps. Maybe you need some minor merging or something like that, or you know, this kind of processes that somehow can funnel gas to the nuclear engines to pass around it. And then with the others as well. I don't know if I answered the question.
Yes, I think that it
Makes sense. Yeah.
Thank you. Alison, this is μπορείτε να μιλήσετε και μετά την κύριε Georgakakis, ευχαριστώ πάρα πολύ.
Ευχαριστώ.